on Tuesday. Okay, so remember, a true statistician would ever just give a point estimate or one value because they would take into account variation. And so if they're going to give an estimate, it's going to be a range of values because, remember, the data could have been different. So in general, for our introductory courses, what we have is we have our point estimate plus or minus our multiplier times our standard error. The standard error is our variation that we're taking into account. The multiplier is how many steps or how many standard deviations or standard errors we would want to be so that we're within a certain confidence interval. So let's talk about one sample confidence intervals. And so it could be that we have categorical data or quantitative data. And this would be if we had a sample. And so our estimate, this is what we would take with our sample. This could be something like p hat, the number of successes over the number of trials. Or our quantitative part would be a sample mean where we would sum up all our values and divide by n. That would be our point estimate if we're trying to estimate the center. There are other things we would want to estimate, but this is how we would get going. The standard error then is how much variation or each step of the variation would be. And in this case, we showed about this in section 5.5 that the variance would be p hat times 1 minus p hat over n, and we take the square root to get the standard deviation of that particular sampling distribution. And our sample standard deviation divided by n, this is what we showed with the central limit theorem, that would be the variance of x bar as a statistic. Finally, what you have to do, because we're going to use some sort of normality check to see if the data is normal, for categorical data, we want to make sure that it's not towards the ends. Like it's not skewed up into the small values or to the large values. And so we want the expected number of successes to be bigger than 10 and the expected number of failures to be bigger than 10. If it's not, then it's kind of skewed and you really can't use a z statistic for your result. For quantitative data, we either want our data could be normal from the begin with, or n bigger than 30, because then the central limit theorem kicks in. That's what CLT stands for. Or use the probability plot to see if the data is plausible that the data came from a normal distribution. Alex?
So categorical data, I'm just having a little bit of trouble understanding what p hat means, because we talked a lot about x bar and things like that, but I don't really remember talking much about p.
Well, this is back in August. Binomial theorem,
right?
Number of successes over the number of trials.
Okay.
Chapter 3 kind of stuff.
Why is that categorical? I didn't realize that was binomial.
Well, it doesn't have to be binomial. I'm just saying that that's kind of where we talk about it. Well, because what's the average of a male and a female? What's the average between true and false?
Okay.
You're either in this category or you're in this category.
All right.
Or you could have multiple categories like that. So that really doesn't make sense to take the average. What you do is you take the number of successes and put it over the number of trials, which would be the number of successes plus the number of failures that you have.
And p hat is your sample proportion.
Yeah, it's the sample proportion. Just like this is our sample mean, this would be our sample proportion. And we're trying to estimate the true proportion. And it might be theoretical. We may not be able to do this thing infinitely many times to find out what this will end up being. So when you get this, you get this sort of formula. And you don't necessarily have to write this down. What you can do is take your Saladrin course pack and look in the back. Which I guess we really don't have to see the light upstairs. We'd probably be better for this. So if you go ahead and look at the back of the baby blue, course, that's large sample. Let's first of all, the single proportion here. Over here on the right, you get the various confidence intervals that you would get. Our estimate times our multiplier times our standard error. Kind of tells you what the notes are. It has to be assuming that your expected number of successes is bigger than 10, greater or equal to 10. Expected number of failures is greater or equal to 10. Over here on the right is the confidence interval that corresponds to it. Whether you want a one-sided, two-sided, or the other left-sided. The other one I guess I would point out to is maybe the forest. Oh, it is on this other side. The first side of the blue one. Here you get your two-sided confidence interval. This part over here, that's going to be next week when we do a hypothesis test. But over on this side, you've got your sample estimate times your multiplier times your standard error. And then you're saying that the mean will be between these two values or bigger than those two values. See, if we had the video, we could kind of look at it this some more, but we didn't. Okay, so what we do is rather than giving a single estimate, statisticians give an interval estimate because, again, we want to take variation. So we're specifying that let's say the true proportion is between these two values, like 52.5% and 61.5%. But we want to know about how much evidence that we would have in that. And sometimes we would write it this way, 0.057 plus or minus 0.045. Smile behind my math for the day if you can tell me what we would call that 0.045. The margin of error. Very good. Very good, Mitch. That would be your margin of error. And again, this is our general formula for if we had a mean, where we had quantitative data. In general, your textbook starts off, this is where most statistics books start off, if we knew what the standard deviation was. But if you think about it, if we knew what the standard deviation was, we'd probably know what the mean was too. So I think it's just to kind of delay having you look at the t-distribution, which we'll see here shortly. So this would be our multiplier times our standard error, and there's our estimate. So again, we're giving a range of values. And again, in the big five, in almost all introductory statistics courses, it's that same sort of idea, sample estimate plus or minus the multiplier times the standard error. Now, when we're talking about this, when we say a confidence interval, we're saying in the long run, if we use this method over and over again, we would capture the true population parameter 95% of the time. Okay? It's not... okay, so it's the method that does it. And if we say 95% we're confident, 95% of the intervals we compute will capture the true parameter, 5% of them will miss it. Lauren?
Can you explain the difference between the T and the Z multiplier?
I will. Very good. Great question. I've got you. I'm going to get you covered then. We're still on the introductory parts of this, but be careful. Do not ever say there's a 95% chance that the mean is in my interval. It's either in there or it's not. The probability is it's 0 or 1. It's not your particular estimate that tells you where there's a probability. It's the method. If you did this over and over again, you would get this. But your one shot doesn't tell you there's a 95% chance in there. Yeah?
So with 95% confidence intervals, if I took 100 trials, could I say I would expect 95 of them to
capture the true parameter?
Okay.
Yep. Very good.
The word expect kind of is weird because it also goes with expected value.
That's right. That's
I
right.
don't know if that was off.
Well, yeah. again, the standard error is just sort of another fancy way of saying the standard deviation for the normal distribution there. Now, just as a side note, if you open up your book to page 280, DeVore spends a little time saying, here's a better confidence interval. It's called the confidence interval score, or the score confidence interval. He makes a pretty compelling point. We are not going to hold you to that one. I couldn't even figure out how Minitab would calculate that. The point there is there's just not one way to calculate a statistics or approach statistical problems. So just so you're aware, on page 280, he has a little finer method for finding the confidence interval for proportion. If n is large enough, it doesn't really make a difference, but we're not going to emphasize what he's doing there on page 280. Okay, so there is a way that you can do this on Minitab, and we'll do this a little bit later. I'll do it now. So if you're at Minitab, you can go to Stat in Basic Statistics and One Proportion. You can either ask for the samples in a column, or you can summarize the data and enter them in. So I'm going to do 16 out of 48 trials. And then I can change what my confidence level will be. I can change it to almost anything that I want. If I want a one-sided confidence interval, I would change this to like greater than or less than. And it also tells me which exact method I could use. I could either use the exact method or the binomial approximation. Generally, I would just use exact because that just seems better to me. And so in this case, my true proportion, we're 95% confidence that the true proportion would be between 20.4% and 48.4% of whatever I was figuring out. So Minitab, and actually your calculator too, maybe not as fast as Minitab, can calculate these parts. Okay. You should check, first of all, for randomness. If you don't have good data collection, your data is probably bad or contaminated. And the other one you should check is for normality. Again, for proportions, expect the number of successes is greater than or equal to 10. Expect the number of failures is bigger than or equal to 10. So let's go ahead and take a look at an example of racial disparity. So this one is actually in we almost got to it on Wednesday. So it is actually in the course pack where we had. So the Kaiser Health Foundation did a study, and this was in June 2020. And for example, about 6 in 10 black adults and over 4 in 10 said they have been treated unfairly due to their race or ethnicity, as opposed to, let's say, 14% of white non-Hispanics. You know, store where they're shopping, restaurant, bar, dealing with police, at work, or getting health care for themselves. And there's some other things they asked as well, being afraid of their background, 71% to 23%. And then the excessive use by police officers, all those things that were issues in 2020. Mitch!
What was the methodology?
Well, that's what we're going to look at here. So what I'm saying is, we would just not say 61%. We would look at the methodology here to see how this was set up and kind of see if there was tracking. I mean, if they had to call some special people, and they did, like when it was June 8th to 14th, random digit telephone samples. So you'd actually also need to make sure who had telephones and who didn't. And also give the percentage points here. And so here, in some sense, are the margin of errors. Like plus or 7 percentage points. So even though they called 1,296. In a specific category, it would be something, maybe something a little different. So those are important things to check to make sure that whether you feel this is part. So, I don't know, any responses to this? Yeah, Mitch?
Wait, so they called in if they felt like there was racial disparity against them?
Mm-hmm.
I don't know, I personally question the methodology because, I mean, if you think about it today, we're often told that it's more racial disparity against race, so they're more like, I feel like they'd be more likely to call in if you're black and they feel it, well, if you're white, you're less likely to call in, so.
No, it's not the person they called. They were called, so you pick up the phone and answer.
Okay.
So it wasn't they called in. Yes,
Okay,
that's.
so different.
Yeah, those polls that you see in the newspaper, or even in sports shows.
So why is it plus or minus 3 percentage points for the number of people they call? I'm not sure. Do you not know? Or
Well, now remember, they're just looking at the statistical portion, not in terms of the people. And the percentage points are from the standard error. And let's kind of see where that's developed from standard error. Okay, that's the margin of error. It's not, the margin of error just comes from the purely statistical side. It doesn't mean this is how much we think we're off, or our methodology is off. It's this part there. So if you take a look at this, African Americans, there were 211. Okay, so N was 211. Let's do a 95% confidence interval. So if we take a look at this, a 95% confidence interval, how much would we put at the tail end? We have 0.95 here. How much would we put, area would we put on the left side, and how much would we put on the right side?
2.5.
Yeah, 0.025. And so we want to find out what z of 0.025 is, which means the point at which past that is 0.025. So in your calculator, go out and calculate what that z value will be. Okay, so which is the command? Is it norm CDF or the inverse Z? Inverse norm CDF. Inverse norm, and what do you end up getting? 1.96. So you do inverse norm of 0.975, 0 and 1. So this is 1.96. So let's go ahead and figure out our standard error. Our standard error would then be the square root of p hat times 1 minus p hat. So let's, the p hat we're saying was 71%. So 0.71 times 0.29 over 211 would give us I think it's like 0.06, isn't it? Oh no, it's not 0.06, it's 0.03 or something. Yes, Jeff?
Wait, what exactly is the statistic we're measuring here? Because isn't it just the numbers of each category?
Within each subpart, and since we're trying to measure the blacks who said that they experienced some sort of discrimination within their life, we're just taking N to be 211. So what did you end up getting? 0.71 times 0.29 divided by 211. Take the square root. You got
0.0312.
0.0312. So our estimate would be 0.71 plus or minus 1.96, so 1.0312, which I don't know how I got 0.301. So for this particular one, what ends up being our margin of error? If you multiply the 1.6 times 0.0312,
106,
is there any sort of like decimals after that?
1,
Okay, well, we'll keep it like this. So this right here is the margin of error. So we would say the true proportion is going to be between 77% and 65%. Howie!
Where did you get the 0.71?
Oh, that's the percentage that they said, 71%. Where did I get the 71%? It was a different statistic that here it is. Yeah.
Wait, so when you're looking at the categorical, what's the X and the S over N?
This one here.
No, in the categorical.
What's the S?
X.
Oh, this is number of successes over the number of trials. Right. Jeff, what was your question?
My question is, if you go back to the table, the other table.
Oh, the other table up there? On figure 1? Oh, this is the 71 I had. So I told you.
The methodology table by the way.
Okay.
Yeah, that. What is the rightmost column in the node?
Margin of standard error.
So what does it mean to have a margin of standard error for a number of samples?
Well, because the sample size is smaller than, let's say, 811. Because the 811 is larger, its margin of standard error, because the n will be larger, has a smaller interval.
Well, so margin of standard error what exactly?
Of something like this,
Yeah, but
the percentage.
There's multiple different either the categories or
I don't think it tells me what that is. Or marginally a sampling error. I'm sorry. Includes the full sample of plus or minus 3 percentage points and key subgroups, or maybe higher. So just because you have a smaller sample size for this, when you break it down, that sampling error is going to be a little bit bigger.
I guess it was like how to think about that because
Well, I mean, something like this, what we just did here, we found our margin error of 0.06. They might have used a 99% confidence interval for that.
well, I mean, like they said that 211 black responded, and then it says plus or minus 9%. So like, what does it mean to have 9% error on the 211 responded?
Yeah, so if we perform this again and again, we would have a sampling distribution with a standard error, right? Right?
Oh, so it's like,
And so when you have more participants, that sampling errors standard deviation gets smaller, right? And so if you take a look for proportion, this area between here since it's percentage, you'll be going up a certain percentage and down a certain percentage.
Can you go back to the
And so it's like 9% up or 9% down or 6% up or 6% down.
Can you go back to the table?
Can I do what?
Can you go back to the table?
Yeah.
So there's 1,300 total, and so the margin of sampling error would be like, you got 211, but if you did it over and over again, then you have like maybe 230 or 200 flat in a certain, if you did the experiment, I guess, we'll call it.
I don't think I'm following you, but if you survey 1,300 other Americans again and again and again and again, like 95 or 99% of the time, we would capture that, and the standard error would be 3% up.
But you wouldn't get 211 every time.
Oh, for if we only took the black participants and interviewed 211 over and over again, 99% of the time we'd capture it. But we still can capture, can calculate the standard error, and using that part, it'd be roughly 3% or 6% or 9% up and down. So you have a statistic. It might be beneficial to sort of ask, friends whether they've experienced such things like this. I would say 4 of the 5 categories. I've been personally experienced by members of my family. So, okay, so let's go ahead and write the confidence interval on the sheet then. We checked the randomness. It did appear that the number of successes was bigger than 10, 150. Number of failures, bigger than 10, 61 per out. So the sample is large enough to approximate it normally. So with 95% confident, P is going to be between 0.65 and 77. And so I'm going to have to interpret this in confidence. So we are 95% confident that between 65% and 77% of all black American adults have said they've experienced some sort of racial discrimination, although I guess I didn't have the right context, because that 71% was a different guy, so you didn't probably pick the right ones. So anyway, I have the confidence level, I have the interval, I have the parameter as the proportion, and then I also have the context. Alex!
So here we're doing like our confidence interval, and we have like 0.95, and we have we're looking at like the tail on either end for Z.
We're trying to find the multipliers. So one of those things that are within 1.96 standard deviations less than the true and 1.96 greater than the mean.
Okay.
That's our multiplier that gives our standard deviations.
Yeah, I just had a question about the randomness. I know that you had mentioned because the sample was taken of people that they called. Is it because it's a great enough sample size? Can you count that it's random, or would that?
If you were a stickler, you could say it wasn't random because it's not all Americans. It'd be only Americans at phones. But you have to be a pretty big cynic, and many times I am a cynic. So the sampling method does need to look at, because you don't have a random sampling, then it's not good. So it may not be 71% of African Americans experienced discrimination. 71% of African Americans said they experienced discrimination.
Is there any way to account in like a study like this for the self-reporting nature of the study?
Right. And that's the question if it's self-reported or not. That's why sociologists have other techniques to kind of sift through those answers. One of the reasons why the polls were wrong in 2016, at least it's been reported, is that people did not want to say that they were going to vote for Trump. And so there's a lot of underreporting. The other part was some said they used antiquated sampling methods because fewer and fewer people had landline phones. The other part is that many new people voted in 2016, and so you have to sort of make those adjustments if you're going to be a sociologist or political party, and so that takes a subjectivity here. Here we're just taking the mathematical part of things. David?
With the categorical standard error, how did we get the formula?
Back to section 5.4. So if you take a look at what we did in on page 67, there we were looking at Bernoulli binomial distribution, and we got the expected value and the variance based on thinking of the proportions as quantitative data. Alex?
So is there a difference if we were to be doing this and we found a multiplier where we...
Remember, if we're going to be more confident, what's going to happen to our confidence interval?
It's going to increase.
Wider. So our multiplier is going to be bigger.
Right, but
We're standardizing everything with the standard error so that every step is a standard deviation. I just call it standard error so it doesn't confuse with the population standard error. So the multiplier tells you how many steps up and down of standard deviations, standard errors you're going to have.
Okay. So, I've seen some things, some images and things where you don't, there aren't, it's not like you're looking at a tail, you're only looking at one tail.
Upper and closer, yeah.
So what is that? Can you contextualize that for me?
Yes, I can. If you let me, I have other slides for that too. Okay. Let's try to look at this example. A Florida student asked 20 undergraduates whether or not they were vegetarians or not. 4 of them said they were vegetarians. What would you say about this study? It does appear to be random, right?
Yeah.
I mean, from a university, we don't know if you just pick people outside the tofu bar or not. So was that? Oh, is that categorical or quantitative data? Categorical, right? You either are a vegetarian or you're not, presumably, or maybe you're a flexitarian. But if you look at it, it is. We'll say it's random. We'll just assume that. But the normality is not valid because we only had 4 successes. And so we can't use our approximately normal, so we really can't do a normal based. We'd have to use something else. So collect a larger sample, and we might be able to use the binomial distribution for that. And there is, like I said, if you use the binomial distribution on Minitab, that will be. Now, the one thing you know is that takeaways is that confidence intervals based on small samples, as long as they meet that 10 greater than, are still reliable, but they're very wide, and so maybe not very precise, or just have a lot more wider intervals. By the way, and don't just assume because you get a confidence interval that the true population parameter is in the middle. That's not necessarily the case. Your net could catch it if it's a little bit skewed to the right or left. So just as remember, for one sample mean, when we're looking at quantitative data, there are 2 possibilities. We can apply it when the central limit theorem kicks in, or if we take a look at something to see if it's plausible to come from a normal distribution. we should always check for randomness. And you have some homework problems that you'll just have to say, I don't know, it doesn't really say if it's randomly selected. So don't just assume or not. So the situation 1 is that if it comes from a bell shape, you don't have to worry about those assumptions. And so any size will work. Or if it's bigger than or equal to 30, remember almost any distribution will start to look normal. And n equals 30 is just sort of our general. Here's the problem. We don't know the standard deviation. So because we don't know the standard deviation, we have to approximate the standard deviation. And since we approximate the standard deviation, we have to go up like 4 or 5 letters from z to t. Okay, so t is going to be our new distribution. Okay, Lauren, here we go. Our t distribution that we have. So again, the general formula is that we have this t as a multiplier. And t very much behaves like z, more or less. And here's the student's t distribution. The one thing about the t distribution is it has heavier tails. Do you have any sort of sense what heavier tails mean? Yeah?
More space on the end.
Yeah. So if this black one's the normal, there's more area off to the left and to the right.
We don't know the sample standard deviation.
Not when you're taking a sample.
I mean, when we're using T.
If you do take a sample, you can calculate the sample standard deviation, but you don't know what the true population standard deviation is.
So the population standard deviation is unknown.
Yeah, the population standard deviation is the one that's unknown. So what that means is that the multiplier will be slightly larger with the t distribution, partially to make up for the fact that we don't know the population standard deviation. So the multiplier is going to be a little bit bigger for the t distribution because we don't know the population distribution. Because there's variation now in the standard deviation, we have to make it a little bit bigger. So there's one other thing with the t distribution. You know do many times the expected value will still be mu. The sampling distribution's standard error will be s over square root of n. But you need to know one more thing, and that's the degrees of freedom. You guys talk about degrees of freedom in engineering? How many? Okay, I mean, just basically you have so many unknowns in so many ways to find those unknowns. With the t distribution, you need to know that you have n minus 1 for one sample. Other distributions, you have different degrees of freedom for t that you need to take into account. So again, the larger the t is, or larger the degrees of freedom, the less heavy the tail is. So the z curve, and then the t equals to 25, and then finally the t equals 5. There'll be more area underneath there, so your multiplier will be larger. But you need to know the degrees of freedom. But the higher the n is, the closer t gets to being normal. So if you have your calculators, I think we're about ready to look at the calculator. So let's suppose that we want to know what t of 0.05 is. I would draw the picture, and I want t of 0.05, but I also have to tell you the degrees of freedom. So this would be an inverse t business because I know the area to the right. Notice it's 0.95, but it also asked me what my degrees of freedom are, and that's the 6. So I paste that in there. I get the 1.9431. So with Z, the parameter you need is the mean and standard deviation. With the T, we're already going to assume that the mean is 0 and the standard deviation is 1. But you also need to know what the degrees of freedom will be. So if you want to do T of 0.05, inverse T of 0.95, 15 degrees of freedom. If you need to know what T of 0.05 is 22 degrees of freedom, you'd have that. And 0.01, you got to fill in a 0.99 area and get the 2.508. Again, because of this kind of way. This is kind of how we represent the multiplier. Alex?
Can you, well, okay, I have 2 questions actually.
Okay.
Can you explain a little bit more what you mean by degrees of freedom? And then secondly, how come our shaded area here is only one tail, unlike before?
Here we're using this shaded area because we're trying to find the multiplier, and this is just the notation that we use. But there's going to be 5% to the right.
Okay.
So there's 5% area here, so we want to find out what this multiplier is, so that to the right of that, there'll be 5% of the area probability. So we're not it's kind of a little different thing than what we did before. The other thing of degrees of freedom, basically you have n equations, n unknowns. You know 1 because the mean goes through it. So now you have n minus 1 degrees of freedom. Okay, if you want to think in terms of engineering examples. I wasn't going to say that, but since you know, I go ahead and did that. And by the way, as n gets larger and larger, like I put in a very, very large number, the t value gets almost the same as the normal distribution. Usually n bigger than 30 is close enough. That's why we use it. But that was also a case when we didn't have calculators. You just had tables. So I think that's the other reason why we look at 30. I think technically you should continue to use the t-score in any sample.
Everything is the same with like the mu of x bar and standard deviation of x bar. Is there anything different with
The multiplier is a different one.
So the proportions are all the same too?
Yeah, those proportions don't use t distribution. They all use z distributions.
Oh, all proportions are?
Yeah.
For what?
Theoretically, by the way the central limit theorem works, it'll become a normal distribution with the proportions. The t distribution is for smaller samples. The central limit doesn't kick in yet, but you can still use something that's a bell-shaped curve or approximately normal.
So it does depend on the size as well? And
Yes, it depends on the size of your sample.
And the lack of knowledge of the population.
That's right. If we knew the population, we wouldn't have to sample to kind of find out more about it. Just as a reminder, because those of you who are in secondary education should also be exposed to the history of statistics. Story was originally called T. Gossett worked for the Guinness Beer Company, and in terms of quality control, and he published his things, but he couldn't use his real name because he was actually working for a company, and so it was just known as Students T. And then later on, they found out it was Gossett. This is not something that we promote here at Taylor Beer Sampling, so we will move on. Let's try another one. For a random sample of n equals 16 college students, reporting hours of TV viewing per day. This is ancient days, like maybe 2 years ago, because none of you watch TV anymore. Not on the TV set. The sample mean was x bar equals 2.4 hours. The sample standard deviation is 1.4. Is this categorical or quantitative? Quantitative, because time is quantitative. So we would take a look at this. So we're in that category of quantitative data. So we could calculate the standard error. The standard error would be 1.85 divided by 16, which gives us our 0.46. Our degrees of freedom is n minus 1. When you're doing a one sample, not a two sample, a one sample, you take one less than your sample size, and we construct a 95% confidence interval for this. However, we need to make sure that it fits the conditions for the t-distribution. Well, is it random? It said it was. I don't know how trustworthy you are about taking randomness, but we'll assume it's random. Is it normal? No. It's not bigger than 16, so we can't use the essential limit theorem. So we have to kind of fall back on to see whether it plausibly came from a normal distribution. And to do that, we use what on Minitab? The probability plot, that's right. So if you look at the data, here it is. Is that normally distributed?
No.
Maybe, maybe not. Could it plausibly come from a normal distribution?
Sure.
Maybe. So we go ahead and plot the normal probability plot. And it is bigger than 0.25. You know, it may not exactly come from a normal distribution, but it's close enough and t-distribution is robust enough that you can go ahead and use the normal distribution. Let's kind of compare that with something that's not normal from a normal distribution, like something like this that's right skewed. Notice that the lines do not line up on a line, and the p-value is less than 0.01. Yeah, Ellie?
So you can't use D or t distribution if the distribution is not normal?
If it's less than 30, and it doesn't seem plausible that the data came from a normal distribution, you have to use something else, which is beyond the scope of this course.
So when you're deciding to use t or z, is that solely based on the information you're given? Like if you're given the mean standard deviation, or if you're given the sample standard deviation?
It's more decided on the size. The size of your sample. If your size is bigger than 30, use z or t, they're close enough. The essential limit theorem kicks in, everything is great. If it's less than 30, you now have to use the t-distribution regardless. You also have, one of the assumptions is that it comes from a normal distribution. Plausibly come from a normal distribution.
So you can't use Z at all when it's under 30.
I mean, not
accurate.
legally. So we did this, and we could calculate that. Let's try another one. Minor league pitcher, time the speed of the first 9 fastballs. This going to be okay? No, because what is it violating? Randomness, right? You're not really taking random pitch fastballs, you're taking the first 9. So it's not very random. So you shouldn't really construct. So it's not valid. What you need to do is, collect maybe a bigger size and try this. Your book has some things on, well, what size should you use? Depends on what your confidence interval you want, and then an estimate of your standard deviation, and then your width. Like your width of the interval or the margin of error, you can do this. Again, Wilson's is kind of in DeVore because he likes his theorem. You can skip that. Just use the approximation for this, and you can figure out your sample size. But I want to get to where, so you just plug in, look at the formula, plug in your multiplier. You generally use 0.5 because that maximizes the parabola, and that's the largest it will be. Like 0.25 times 0.75 will be less than 0.5 times 0.5 because you have a nice little parabola. The top is going to be maximize that is 0.5 times 0.5. And this is kind of the reason why you would want a one-sided confidence interval. If you want to build a levee to keep out the water, and they say we expect the water to crest at 102 feet. Well, first of all, I want to know what the variation is. I don't care if it crests at 98 feet. I only want to crest at what's the highest it's going to be within our 95% confidence interval. So this would be the situation, to err on the side where the water could be higher. Oh, I was going to show you about farm salmon. Essentially, it's very easy to calculate on Minitab. All you have to do is go to Stat, Basic Statistics, in this case, Sample T. And I'm going to say within a column. Hey, how come you're not in there? I have to click the column.
Click in the box below that, and then make it pop up. No, in the.
This here? Oh yeah, Myrex. I can change my confidence interval. And I want to say that it's less than a certain value. And that can give me a confidence interval pretty quickly. Okay, if you could line up alphabetically, and except for I screwed these up, so don't have to line up alphabetically. You can just pick up your test as I call out. David, Jeff, Shane, Gabe, Clay, Rose, John,